Electromagnetic waves exhibit varying speeds of propagation as they traverse different materials, a fundamental principle in understanding signal behavior within printed circuit boards, PCBs. The substrate material of a PCB dictates the speed at which signals propagate. However, at super high-speed transitions, the rate of change of the signal outpaces the substrate's propagation speed. Consequently, this leads to a phenomenon where the transition slows down as it propagates along the trace. This deceleration effect gets transmitted along the trace, resulting in the attenuation of short-duration pulses. Furthermore, this discrepancy in propagation speeds induces microreflections, contributing to signal distortion. The plot depicts the delay at 1 mm intervals across a printed circuit board employing an FR4 substrate. Highlighting the propagation characteristics of signals, the plot features a dotted line representing the predecessor curve, delayed by the same time as the succeeding curve. The difference between the dotted line and the solid line illustrates the change induced by the propagating signal. As the signal traverses along the trace, this disparity accumulates, resulting in the curve gradually accumulating over distance. This initial curve is a consequence of the variance in speed between the source signal and the propagation medium. When the pulse duration is not significantly longer than the initial curve generated by signal propagation, attenuation occurs. This attenuation phenomenon manifests as the pulse traverses down the trace, gradually losing its intensity. The pulse's attenuation accumulates over distance, resulting in a reduction in its magnitude as it propagates along the trace. This effect is particularly pronounced when the pulse duration closely aligns with the initial curve's duration, leading to a progressive diminishment of signal strength along the transmission path. When employing a faster substrate material, such as air in the construction of a printed circuit board, the propagation delay experienced by signals is significantly reduced. This reduction in propagation delay is a consequence of the higher speed at which electromagnetic waves travel through air compared to traditional substrate materials like FR4. Additionally, the initial curve generated by the signal propagation is also shortened due to the reduced propagation delay. As a result, signals experience quicker transit times and shorter durations of delay when traversing through air or similar high-speed substrate materials, leading to enhanced signal integrity and faster circuit performance. A shorter initial curve allows for less signal attenuation. When non-conductive water is used for the printed circuit board substrate, both the initial curve and the propagation delay are increased. In this example, it takes about 130 picoseconds to traverse 5 millimeters. This increase in the initial curve duration creates more attenuation. When developing a super high-speed printed circuit board, it's crucial for the developer to understand how fields propagate within the materials used. Neglecting to consider field propagation can lead to false solutions based solely on circuit analysis or past experience in different circumstances. Without a comprehensive understanding of how electromagnetic fields behave within the specific substrate materials and layout configurations, developers may implement solutions that fail to address the underlying propagation issues effectively. By prioritizing an understanding of field propagation dynamics, developers can ensure that their solutions are tailored to the unique characteristics of the printed circuit board, ultimately leading to more accurate diagnoses and effective optimizations for high-speed performance.